Hello all, welcome to the module. This course is on mathematical modeling of biomedical systems and biomedical devices design. Till now, you have thought how mathematical modeling can be done for different types of biomedical tissues and systems and their underlying principle. How those principles can be used to analyze the signals that you get from the biomedical devices. In reality, how do we get these signals? How do we interface those signals to electronic systems for further analysis? So these are some of the questions that we always have to think when we are designing a complete system. So if you look into any device or the system, it consists of input and output. It need not to be only for the system or a device. It can be any subsystem of a system too, where any system, if you can divide into multiple subsystems, each subsystem will have its own functionality. Combining together, it will form a complete system, right? No matter what, whether it is an individual system or whether it is a subsystem, it will always have inputs as well as an output. So what is an input here? An input is what we are trying to measure or what we are trying to analyze, whereas an output, it gives you the information about the input in order to communicate to the next corresponding system, or if it is an end user, the output whatever the system is providing will be relevant to the input and where the end user can understand it, right? But in order to do all these things, the input system should have a ability to understand what is the parameter that is going to be measured in the real world. For example, say when we are dealing with these biomedical systems, so when I say a system, electronic system, which means that this complete system uses an electronic component, whereas a biomedical related input is nothing but in the form of different physiological principles, right? It generally will not be in the form of where electronic circuit can understand. So the first subsystem when you look into these electronic system designs would be a transducer. Let me give you a brief idea about the difference between a sensor and transducer. You might have already heard about a sensor, you might have also seen people will intermittently change the word as a sensor or transducer, both way they consider it as same. But there is a small difference between a sensor and the actuator, sensor and the transducer, and actuator and the transducer too. In reality, the transducer is a device which converts any form of energy into one form of energy into any form of energy. One form to the another conversion, if it can do, it is called a transducer. Whereas a sensor which converts one form of energy into an electrical output, whereas an actuator is nothing but an electrical output, electrical input will be converted to a mechanical action. So that's why when you look into actual terms of the sensor and actuator, a sensor is generally being mentioned it as an input transducer, whereas an actuator is an output transducer. But why do we have to discuss about this? Whenever we are trying to analyze the signal that is being acquired by an electronic system, the parameter or the input measurement always will not be in the form of where the system is capable to understand it. So in order to have a bridge between the actual physical measurement to the electronic system unit, we always have to use some kind of a sensor that converts the input measurement into an electrical signals, where the next part of the electronic circuit design, electronic circuit systems can understand it. So today's session, what we are going to see is that, as in the previous sessions we have already discussed about how to how do we mathematical model different biomedical tissues and the system and their underlying principles, how do we get these signals? How do we interface those signals to electronic systems for further analysis? What is the need of signal conditioning circuit? So, all these parameters, all these topics we will be discussing in today's session. So, as I told you, as I briefly explained to you about a complete system point of view, in general you will always have a sensor that converts your input physical parameter, physical measurement into an electronic system understandable signals. So, even in this case, if your input is your biomedical signal, the output will be in the form of electrical output voltage. So, you have input as well as an output, and that will be connected to a signal conditioning circuit followed by an ADC. So, the idea of this ADC is, in this digital world, if you want to interface or if you want to communicate faster or if you want to store the data, analog signals consumes a lot of energy, lot of resources and everything. So, the one easiest way to do everything in a small robust environment is by using microcontrollers or digital platform. But whereas the real world signals will be always in the form of an analog, in order to do that processing we should have to convert analog to digital conversion. But again, if I consider it as a subsystem where the output from the sensor is nothing but an input to the signal conditioning circuit, and output of the signal conditioning circuit is an input to the analog to digital converter, you may ask a question, why can't we directly interface the sensor to the ADC? Of course, we can do that, but we do not know whether the output of the sensor is capable to directly interface to analog to digital converter. So, in case if it is not capable enough, then we require to use a signal conditioning. When I say capable here, multiple factors that we have to keep in our mind when we are interfacing. One is the levels, the output level of course, when I say a system, output side of the sensor system, sensor device which will be completely electronics, anyway the sensor is also in the form of an electrical output voltage, where this the next level of subsystems will also deals with the complete subsystem electrical signals. Where is the complexity in interface? The complexity lies between the signal amplitude, signal isolations and levels, matches, whether it has a very good match with respect to the input and output. So, all these factors will comes into an effect when we are to make us aware whether this sensor output can be directly interfaced to the next system or not. In case if it is not, we should always have to build another interfacing system or a signal conditioning circuit in order to act as a bridge between your previous system to the next system. So, the major role of these signal conditioning circuits will be amplification, isolation, filtering, excitation as well as linearization. So, these terms you would have already heard, you may be knowing the definition, but how do we design is what we are going to see in this today's session. Of course, in the last session you have already we have already introduced you to the simulation software, where once you design the system, once you design according to your input and output, how do we analyze the system performance, whether it is up to our requirement or any deviation from our requirement or not. So, those simulation software will be helpful to us to further analyze the design system, right. So, when I talk about most of the industrial application, so no matter what your sensor data, if you want to directly interface to a microcontroller or a digital platform, you should always have to follow certain intermediate steps in order to match between the both the things. So, in this case, in this industrial application, for example, say you have to measure some temperature of certain process. It can be body temperature, or it can be some other industrial application when you see a temperature of a boiler or a unit. So no matter what, when you look into that, when the input measurement is to be of is to measure the temperature, which is not in the form of an electrical signal, that temperature, because temperature physics is completely different than the electronics that we use. So you will always use a sensor that converts the temperature information about the temperature into electrical output voltage or a resistance change, which is directly proportional to the temperature. That change we cannot directly interface to an ADC, because the output voltage, for example, if you take LM35, the temperature when you look into the sensitivity factor of those sensor, it will be very less, somewhere in the range of 10 millivolt per degree centigrade, right. So such a small voltages, when we directly interface to the ADC, the major problem would be the accuracy you are compromising on the complete accuracy of the system, right, or the resolution of the system you are compromising on. But if you are looking for a very good resolution data, very good resolution data, you require to use some kind of a bridge circuits to understand the mismatch between your input and output, and create a circuit such that mismatch can be completely removed, compensated, right. So that is nothing but your signal conditioning. But you may ask me a question, what is the need of 40 to 20 milliamps transmitter and the receiver when we are interfacing to an ADC? The reason why they use is that they may, in case when you are when your sensor is somewhere remotely located to your digital platform or the analyzing circuitry. For example, say in this case the analyzing circuitry is your a microcontroller. When we are directly transmitting the signals from the output of a signal conditioning circuit, which is in the form of voltage, to directly interfacing it to an ADC over a cable, due to the resistance offered by your long cables, there will be a drop of voltage, right. When you are having a voltage passing through a resistor, because when I consider each cable will have its own resistances, there will be a chances of there will be voltage drop across this resistance, and finally you will end up having the loss of a data. As a result, any losing information of the input is nothing but you losing the information of the input measurement. So in order to compensate for that, rather than transmitting the input information over long cables using an voltage, if you use a current as an input, since it will be in a series form, if you have a multiple resistors connected in series, each resistor will be the current flowing through the complete series circuit will be the same. The loss of data will be zero, very less, negligible when I consider it. As a result, you don't have to compromise on your accuracy, or somehow you have to understand what is the loss being created by the transmission of signal over the cables, and you have to somehow compensate for these transmission losses. But one simplest way is to convert the output information, output voltage, which is the information about the temperature, into a current form and transmit over the longer cables, and again use some kind of a receiver where it again converts your current to a voltage. So that is nothing but your 4 to 20 milliamps of a transmitter, where the signal conditioning circuit in this case not only amplifies your temperature input, it also converts your voltage information into a current and transmitting over a longer distance remotely. Then again there will be a receiver where it will understand what is the current being recorded, and then uses a signal conditioning circuit that converts your input current information into a voltage that can match with respect to the input ADC levels. If that does not match, again you are compromising on the accuracy of your ADC. You are not utilizing the complete levels of your ADC, you are compromising the sensor your ADC's capability. So then as usual, then your microcontroller, once ADC performs the conversion of your input signal to digital, then digital controller takes the lead and does the complete processing according to the requirement. And in case if you have some kind of an application where based upon the input that you have analyzed, you have to actuate something. So then as a microcontroller again deals only with digital signals, and your real world signals cannot deal with the digital. You have to convert that the digital to analog platform using some kind of digital to analog converters, and moreover this digital to analog converters cannot provide enough power that is required for your actual actuators. As a result, again they use some kind of a signal conditioning circuits kind of a to match the power, input power with respect to the output power, and transmitting as usual, as we have already discussed in the previous section. Why do we need a 4 to 20 milliamps of transmitter and the receiver? Transmits that, and according to the actuator of your system, that performs signal boosting or signal conversion, where heater can respond according to the input signal. So this is a typical application, a closed loop complete system, where we will understand the input, and based upon that microcontroller analyze and actuates according to the input that we receive. But when you look into the complete system, it is not so complex. At the same time, it is not so simple too. You have a multiple subsystem, and when we are dealing with the individual subsystems, the input of the subsystem should match with the previous stage, as well as the output of the subsystem should match with the next stage. So we should always have to look about what is the input being received, and what is the output that we have to give it to the next system in order to not to lose any information from the input side, so that the actual information will not be lost, should not be lost. So this is the whole idea of the use of a signal conditioning circuits, no matter what, whether it's a biomedical signal conditioning systems, or biomedical devices, or biomedical systems, or it is an industrial system. Any system will always have to follow this logic of understanding the input as well as understanding the output part. So when you see, there are different types of sensors. As I already discussed, most of the sensors cannot provide you the signal that can directly match with respect to the ADC. So to understand the mismatch between both the systems, and creating proper bridge between both the functions, is the role of the signal conditioning circuit. So when I briefly describe about fundamental functions, one advantage of having signal conditioning is amplification. So you can amplification, isolation between your input stage and the output stage. When the recorded signal has a noise, the signal conditioning system should have ability to filter out the noise and extract the useful information from the actual data. Then in few cases, when you see, not all the sensors or not all the transducers can provide an output in terms of voltages. So when I say a sensor, it can be any electrical signal. What I mean by that is that the output variation need not to be always an voltage. It can be any change in the resistance, any change in the current, any change in the inductance, any change in the capacitance too. But it is an electrical change, electrical parameter change. But the change offered by the sensor cannot detect by the ADC, because ADC requires only voltage as an input, or in the next stage whatever we do cannot identify the changes in the resistance or current or inductance or capacitance. So sometimes it is also required to convert the change in the current or the resistance or the capacitance or the inductance into voltages too. So such a way you require to have an excitation voltages. Then linearization, in case if the data that you receive is not a linear, and if you want to make it a linear so that it is easy for further processing, some kind of a linearization techniques also will be implemented, which will be falls under the signal conditioning circuit too. Now for example, say imagine we have a sensor which gives an output voltage, which gives an output in terms of a resistance change. For example, as we have already discussed, one such example as a temperature sensor. When I say LM35 is a semiconductor based temperature sensor, where it will directly gives an output in terms of voltage. But we have also seen all the sensors need not to give an output in terms of voltages too. For example, say if you consider RTDs, for example say PT100, PT100 will give an output in terms of resistance change. Thermistors, that also gives output in terms of a resistance change. That means any change in the temperature will changes its resistance. 8590, which is also another type of a temperature sensor that gives output in terms of a current change. So imagine given the situation where you don't have an output change in terms of voltages, but where you have output change in terms of resistance or current, or even if you have an output voltage of 10 millivolt per degree centigrade, where every 1 degree change in the temperature will change the output by 10 millivolt. Given you this situation, and if you directly interface this 10 millivolt to an ADC, imagine how much how many levels of ADC that you are going to utilize and what is a complete system. Or given you another situation where you always have an offset, for example say you have the output voltage of the sensor will be between 1 volt to 3 volt, the span of your ADC somewhere around 0 volt to 2 volt. Right. So when I directly interface 1 volt the range of sensor directly to the ADC, this is the ADC span, whereas the ADC this is the output voltage from the sensor, span of sensor. So when we directly interface, so it has even though the change, the offset, the change between the maximum, the minimum is 2 volts, and the ADC is also capable to measure the 2 volts. Because of this 1 volt offset, the ADC cannot measure a complete range, that output range that the sensor is providing it. So as a result, because of these mismatches, you will be losing the data, or the accuracy of the system is the range of the system in this case is completely compromised. But if we can somehow increase, somehow compensate for the offset created by the output voltage, such that subtract the complete voltage with the 1 volt, so that the complete span of the sensor will be now 0 volt to 2 volts, will completely match with respect to the ADC span. When we directly interface during such a situations, right, you don't have to even compromise on your the range of your ADC too. So such a small variation, such a small understanding the difficulty when we are interfacing and compensating according to that, right, is the role of a signal conditioning, so that you can accurately measure and you can improve the complete system accuracy as well as the range too sometimes. So in this case, when I deal with 10 millivolt, right, so when you say your maximum temperature to be measured of 50 degree, and when you look into the output voltage, you will get somewhere around 0 volt to 50 into 10 milli, that means 500 millivolt, 0.5 volt. So even though you have a range of ADC of 0 to 5 volts, right, you could use only 0 to 0.5 volts. So see how many levels. Suppose say if you are taking ADC of low bits, right, this 0 to 0.5 volts will be fall under either variation in 1 bit or 2 bit, not more than that. Or if you want to if you are looking for very good resolution of the complete system output, you have to go with a higher bit. Rather than doing that, if we can amplify the input voltage signal by a factor of 10, so that 0.5 will be multiplied with 10, so that you will get a 5 volts. And if you map with respect to the levels of map with respect to the range of your ADC, finally you can utilize the complete levels of an ADC, and the complete accuracy of the system will be improved with a lower bits of your ADC itself. So that is the role of a signal conditioning circuits in most of the interfacing systems. Okay. So now so we have seen some example with respect to when there is a change in the output and when there is a change in the levels, when there is a difference in the levels. For example, say you have a temperature, you have a sensor which gives a resistance change, and you know that resistance change you cannot directly interface to an ADC, right? You cannot interface to an ADC. So how do we do that? So imagine this is your sensor. So the arrow indicates that it's a variable, right, RS. So RS represents the sensor resistance. How do I convert into a voltage? So you should always think about the conversion of resistance to voltage. So resistance to voltage conversion is also a part of a signal conditioning circuit, where it is creating a bridge between the output of your sensor to the input of your ADC. Hope you may not get enough thoughts about this right now, but when I discuss about what are the different ways, you understand that these are the basic circuits that we have already dealt in 10th class or 12th class. One simplest way to convert your resistance to voltage is by using a simple resistive divider network. So imagine I put this resistance in a resistive divider network, where the Vin is the input provided to the system and R is your fixed resistance and RS is the sensor resistance. Now as you already know the calculations of the resistive divider network, we know that V naught is nothing but Vin into RS divided by RS plus R. That means what we can see, suppose if Vin is fixed, RS, which is a base which is the resistance offered by the sensor, which will be always varying, and R is fixed, we can clearly see that V naught is proportional to RS by RS plus R. Right. So if RS and R is equal, then the V naught will be Vin by 2. Right. So this R not only helps to convert your resistance change offered by the sensor to a voltage, it can also be used as a current limiting circuitry or a protection circuit for your sensor too. So both requirements, one is the in order to avoid to operate for a higher currents, as well as to convert your resistance to voltage, a simple resistor can help you to do that too. So but designing the resistance value, choosing the proper resistance value is always important. That depends upon the power requirements of your sensor. But our whole idea was to convert the resistance. Of course, you have already done that. So why don't we directly use this resistance to voltage conversion and directly interface it to an ADC? Yes, of course you can do, but one catch here is that when you are looking into the resistance to voltage conversion, the minimum voltage that you will get will be Vin by 2, or the maximum voltage will be Vin by 2. It depends upon where your RS is being connected and where is R is connected and where the output voltage you are measuring it to. So that means the total range will be half of your input voltage. So that means half of the levels, or for example say my RS is 1 kilo ohm, right. So R I am considering as 1 kilo, where Vin is nothing but 10 volts. So V naught will always start from, see RS, when I say 1 kilo ohm, this is the base resistance offered by the sensor, which means any change that you observe will be with respect to 1 kilo, right. So 1.1 kilo, 1.2 kilo. So the change is 200 ohms, 100 ohms, but the base resistance will also added up into your change. So that base resistance is nothing but 1 kilo. So the total V naught will be Vin by 2. That means the output voltage will start from 5 volts to 10 volts. What is the total range that you have? A total of 5 volts. But what is the span of ADC? Suppose if the ADC range is 5 volts and the ADC is operated at 5 volts, the total span of your ADC input is of 5 volts. Of course, the change that you observe is also 5 volts, but ADC range is also 5 volts. It may match, but due to the offset, initial offset from the resistor, base resistance and the resistance that choose by the sensor, you cannot directly interface into this. But how can we compensate for this effect? Simplest way is offset the output voltage from the resistive divider network with 5 volts. So, in order to do that functionality, we have a different electronic circuits. Again, a design of signal conditioning circuits plays an important role. One way in order to avoid that is to remove this offset is by using operational amplifiers. The reason why most of the signal conditioning circuits uses an operational amplifiers is that it has very good specifications in terms of input impedances, output impedances, CMRR. Because of this inherent properties of the operational amplifiers, most of the signal conditioning circuits utilizes op amps as a one of the crucial part in the circuits. So, the reason I will tell you simply. For example, I have a resistive divider network and the output is connecting it to a system. When I talk about any system will consume some kind of a current and by providing some kind of voltage. That means, it will always have some kind of input impedance. Input impedance and output impedance are some of the important characteristics of any system. So, when I say the input resistance or input impedance of the system is of 1 kilo ohm. So, this is also 1 kilo, this is also 1 kilo and this is of 10 volts. What will happen? You are expecting to see an output voltage of 5 volts, but you may not get output in term the output when you measure now it will not be 5 volts anymore. That is because of the input impedance offered by the next systems. But replacing the system with directly connecting the output of the resistance divider network to an terminal of an op amp will solve your problem, because op amp has a very high input impedance. That is why when you consider a multimeter directly connecting across this terminal, you will not see any losing of the data. The reason is any measurement circuits will always have the very high input impedance. You can further refer into the data sheet of the measuring devices, where they will always specify in terms of mega ohms of your input impedance. The intention of having a mega ohms is that the current drawn by the circuit will be very small. Ideally speaking, it is 0. So, whatever the current that you are getting will not have any change in the input current and the output current because of connecting a simple external circuitry. That is very much important when we are designing a signal conditioning circuit. There should not have any mismatches or drawn by the current or the power consumed by the input source. As a result, if there is consumption of the power from the input, it can be in terms of voltage or the current, the information of the input will be lost when you are transmitting into the next stage. So, this is nothing but your loading effect. So, when we are designing a circuit, make sure that it is not loading your input. When it happens, you are losing the information. So, that is the major characteristics of any subsystem when we are interfacing between two different subsystems. These always have to be remembered. So, we have already understood that the input impedance of the system should be always high. Good. Now, so this is 10 volts, 1 kilo, 1 kilo. So, what I will do, rather than me directly, now imagine that I have a 10 volts. So, what do I get if it is 1 k 5 volts, and most of you are aware with operational amplifiers, I hope. So, when we are dealing with inverting amplifier configuration, so where right. So, the output voltage when there is a increase in the resistance will be in terms of 5 to 10 volts, imagine. So, because V out is nothing but V in into Rs by Rs plus R. So, imagine this is 10, Rs is say 1.1 K and 1.1, so 2.1 K, which is equal to 5.238 volts. So, any increase in the resistance will automatically increase your output voltage too. That that we can clearly see that. Now say I want to offset it, right. One way of offsetting is, say if I connect it, this is 1 kilo V naught. So, instead of connecting here with a ground, if I connect it to 5 volts and say this is V in 1. So, what will be the effect? So, when we solve this, V in minus 5 divided by 1 k. Okay. So, just to solve this, I will consider input as VO1. Now, let me try to solve this. So, it will be V in minus VO1 divided by 1 k is equal to VO1 minus V naught divided by 1 k. 1 k cancel. So, V in plus V naught. So, I am taking V out in this direction, VO1 in this direction, which is equal to 2 into VO1. So, since I need V naught, when I am taking V in this direction, 2 VO1 minus V in will be the V naught. So, since in order to utilize the complete levels of an ADC, we require to use 5 to 10 volts, we should convert this 5 to 12 volts to 0 to 10 volts, adding a 5 volts as a VO1 as an offset voltage makes a V naught to be 10 minus V in, which means that when an input voltage of 5 volts, when the input voltage of this 5 volts is connected here, for a V in 1 which is a 5 volts, that implies V naught we will get it as 5 volts, whereas for input voltage of 10 volts we get V naught as 0. Of course, it is converting 5 to 10 volts to 0 to 5 volts, but it is in a reverse fashion, which means that 5 to 10 volts is converted to 5 to 0. If this is okay, we can simply use a VO1 as a 5 volts, but this reversing order, again in the next stage we may have to compensate for this reverse order, else the results would completely change. Or even in the microcontroller programming, if in case if we use, so we have to compensate for this reverse order swapping. So, rather than that, if we can design another way of using it is, instead of using VO1 as a 5 volts, considering VO1 as a 2.5, right. So, when we consider VO1 as 2.5, considering the case 2, so V naught is equal to 2 into 2.5 minus V in, which is nothing but V naught is equal to 5 minus V in, 5 minus V in. So, case 1 again, when V in 1 is equal to 5 volts, that implies V naught we get it as 0, whereas when V in is equal to 10 volts, V naught we get it as 5 minus 10 minus 5. So, this gives us a negative 0 to, so 5 to 10 volts is being converted to 0 to minus 5 volts. Of course, this is negative since we are using an inverting amplifier configuration, because of which we are getting a negative sign. However, again this negative sign can also be inverted by using a simple inverting amplifier configuration with a gain of 1. So, what I mean is that if I use another inverting amplifier configuration, here the gain is here the offset voltage is 2.5 volts, 1 k, then V in, then again I will be considering one more inverting amplifier configuration with a gain of 1 k, right. So, for input voltage of 5 to 10 volts, we will get an output of 0 to 5 volts within the same phase, because single operational amplifier, because of an offset and because of inverting amplifier configuration, though it is providing the required voltage 5 to 10 to the offset of 5 volts, which the offset of 5 volts can be completely eliminated, but it is creating an shift in the signal. So, to avoid the phase shift, again if you use an inverting amplifier configuration where it has a phase shift of 180 degree, because of that phase shift again the minus will convert to the positive. So, 5 to 10 volts can be directly used as 0 to 5 volts. This is one approach, right. So, as we have already discussed previously, one advantage as we cannot directly connect the V out terminal directly to the V in. The V out cannot be directly connected to the V in because of the input impedance offered by the system. So, one way to avoid the problem is as we already seen, we can use a simple inverting voltage follower configuration where the input will be directly connected, that means the output of the resistive divider network circuit. So, can be the output of the resistive divider network circuit can be directly connected to the positive terminal, and since it is connected directly to the positive terminal of an operational amplifier, the input impedance of the complete system is also high, because the non-inverting terminal or any terminal when we are directly connecting it to the terminals of an operational amplifier, the input impedance will be very high. If you look into the data sheet, it will be somewhere around 10 mega or even more, it depends upon IC that we have considered. Then the output can be directly connected it. So, this solves the problem of input impedance. At the same time, this offset which is being generated by this resistive divider network circuit can be completely removed or completely eliminated with the help of another two operational amplifiers too. So, let me redraw the circuit. So, the final circuit will look like as follows: 10 volts, 1K. So, if I see this is a sensor, this is also R, this is also R. R, what I mean in the sense in initial base resistance. So, we use voltage follower configuration, then we use inverting amplifier configuration with a gain of with an offset of 2.5 and RF by R1. Of course, it depends upon the gain that you require, you can adjust the RF and R1 values. This is R1 and this is RF, so that in case if you require a higher gain and if you want to utilize the complete levels of an ADC, this gain the amplification will always help. And to remove the offset, to remove the phase shift, again we use another operational amplifier with a negative feedback configuration at the same time with a gain of 1. Right? This will completely solve. This will completely convert 5 to 10 volts, which is having an offset of 5 can be removed, and we get achieve 0 to 5 volts as an output, linear varying output. Great. Of course, when you look into that, is this only the configuration that we can build? No, of course, there are different ways of doing this. This is one approach. Another approach would be optimizing the complete circuit. What I mean by optimization, in this case if you observe the number of operational amplifiers that we use or the number of resources that we are using it. Why do I have to consider this? Because when you say a 2.5, so the complete circuit is operating with a 10 volts. When I consider it, again you either have to design another circuit that can provide output as a 2.5, or you have to consider another voltage source to have an output voltage of 2.5, which can be provided as an input to the positive terminal. Of course, you can use another resistive divider network configuration to do the same. So, because of which the number of elements or the number of resources that you are utilizing in this circuit is high. Right? One way to optimize is, instead of using a simple three different operational amplifiers, we can simply go with a simple non-inverting amplifier configuration too. Since in case of a non-inverting amplifier configuration, as the output from the previous stage will be connected directly to the input of the non-inverting terminal of an op amp, this solves the loading effect. This solves the problem that we faced in the previous case, which is of low input impedance. So, how the circuit looks like? So, one way is using this. So, say this is R, this is also R, but this is a sensor and this is a 10 volts. Of course, we have to design the circuit, we have to select the resistance in such a way that this 5 to 10 volts will be converted into 0 to 5 volts. So, but when you look into the non-inverting amplifier configuration, as everybody would have aware, so operational amplifier should always be in a negative feedback configuration in order to reduce the gain of overall gain of op amp, and whereas the non-inverting terminal which is connected to R1 resistor should be always connected to the ground. So, instead of connecting it to the ground, just I will consider this as VO1, this as V1. So, this is also say V1. Now, if this is the case, so as we have already seen in the previous one, so V naught, okay, solving for the V naught, we know that if I say this is I1 and this is IF, so I1 is equal to IF ideally speaking. So, VO1 minus V1 divided by R1 is equal to V1 minus V naught by RF. So, taking V naught in this direction, V1 in this direction, 2 V1. If R1 is equal to RF, R1 can cancel together, or let I don't consider R1 and RF as same. So, R1 RF. So, if I take it in this direction, VO1 by R1 plus V naught by RF is equal to V1, if I take a common, 1 by R1 plus 1 by RF. So, since we require to get a relation between V1 and VO1, so taking VO1 in this direction, which will become V naught by RF is equal to V1 into RF plus R1 divided by R1 RF minus VO1 by R1. So, that implies V naught is equal to V1 into RF plus R1 by R1 minus VO1 by R1 into RF. So, this can be rewritten as V naught is equal to V1 into 1 plus RF by R1 minus RF by R1 into VO1. This is what we got. So, now what we have to do? We know that when we have to design, we have to select a proper offset voltage of VO1 as well as the resistance values of RF and R1 in order to achieve, in order to get output as 0 for 5 volts and output as 5 for 10 volts. So, in order to do that, so let us, for a simplification, I will consider RF is equal to R1. So, when I consider RF is equal to R1, so we can write it down as V naught is equal to 2 V1 minus V1, which is similar to what we have seen in the previous case, right. Now, what we need? Case 1. What should be the value of VO1, and in order to get V naught as 0 for a V1 as 5 volts. So, when I consider this, V naught is equal to 2 into 5 minus VO1. So, V naught is equal to 10 minus, if I consider 10, yes, I get 0. So, for input of 5, I get 0 again. Then another one, case 2. When V1 is equal to 10 volts. When V1 is equal to 10 volts, we should get 5 as an input. So, when I say V naught, so it will be 2 into 10 minus 10. So, which means that 20 minus 10, we get output as 10 volts. So, what is happening here? Here 5 to 10 volts is being converted to 0 to 10 volts, but what we require 5 to 10 volts should be converted to 0 to 5 volts, but it is having an amplification, of twice that of what we have seen in the previous case, right. But using a single amplifier, operational amplifier, connecting directly the V1 output to the input of non-inverting amplifier, we can avoid the use of voltage follower configuration. And if this 10 volts, 0 to 10 volts is good enough, we can simply use a single operational amplifier to solve the problem, right. So, this is another approach of how we can solve this. Next, is this the only way? No, you have, of course, if you want to reduce the offset, if you want to reduce the gain, again at the output stage you can have an attenuator with a gain of 1 by 2, 0.5 with a gain of 0.5. So, that the 10 volts into 0.5 it will become 5, right. So, you can remove the offset, or if you can properly choose the values of RF and R1 such that any voltage when the input voltage of 10 volts to get an output of 5, properly choosing your RF and R1, we can even solve that problem too, right. So, this is another approach. So, this is what we have seen in the effect of loading and input impedance, why it plays an important role when we are designing, when we are interfacing two different subsystems, and if those subsystems are not matching with respect to the loading parameters, with respect to if those input and outputs are not matched, the output will drastically change. The expectations that the output voltage will not be within the limits of what we have planned to design. So, as we discussed, one way to avoid this problem is by using voltage follower configuration, or instead of using a inverting amplifier configuration, just go with a non-inverting amplifier configuration.